All right, guys, going to shift gears a little bit here. Let me ask you a few questions that you should know the answer from grade 1, maybe even kindergarten. Having a little bit of trouble with these. We have kindergarten in the school now. We can pop down and ask a kindergarten teacher to help you out. What's 1 plus 2? Wow. No trick to it. What's 1 plus 2? Leah, what's 1 plus 2? Good. Notice you said that 3? I think. Yes, Leah, it's 3. You're absolutely correct. 1 plus 2 is equal to 3. What's 3 plus 4? Tyler, what's 3 plus 4? 7. Good. Tyler, Leah, did you hear how confident Tyler was when he said that? 3 plus 4 is equal to 7. Like he was sure 3 plus 4 is equal to 7. And that's a tougher one too, Tyler, than 1 plus 2. What's 6 plus 3? Derek, what's 6 plus 3? Maybe. According to the rules of addition that you learn in grade 1, 6 plus 3 is absolutely equal to 9. So we'll give it to you. But in kindergarten, in grade 1, you learn to add scalars together. Although your kindergarten grade 1 teacher didn't tell you you were adding scalars together, that's what you were adding together, right? They were all positive numbers. 6 plus 3 is equal to 9. Later on, when you got to grade, I don't know, grade 5, probably grade 6, you learned that 6 plus 3 wasn't necessarily equal to 9. 6 plus 3 could have been equal to 3, or it could have been equal to negative 3. It depended upon what sign the 6 and the 3 had. 6 plus 3, if 6 to the north, 3 to the south would be 3 to the north. 6 to the south plus 3 to the north would give me 3 to the south. So it'd be negative 3, right? Sometimes 6 plus 3 is not equal to 9. And Leah, in fact, sometimes 1 plus 2 doesn't equal 3. It could have equaled negative 1. Sometimes 3 plus 4 doesn't equal 7. It could have equaled 7 or positive 1 or negative 1. Okay. According to the rules of scalar addition, which you guys all said is correct, according to the rules of vector addition, the numbers can be different. But you guys have seen those rules. You might not have called them the rules of vector addition before, but you've learned that 3 plus 4 can equal negative 1 if the 4 is a negative number, right? Have you guys seen that before? 3 plus negative 4 equals negative 1, right? What if you're not talking about 3 to the north and 4 to the south, or 3 to the south and 4 to the north, but you're talking about 3 to the north and 4 to the west? How do you add those numbers together now? Right? 3 and 4, not paying attention to direction, is 7. 3 and 4 paying attention to direction could be 7, or it could be 1, or it could be minus 1, or it could even be something different. It could be 5. How do you add those together if you have, let's say, 3 to the east and then 4 to the south? How do we add them together? Not equal to 7, not equal to 1, not equal to minus 1. It's equal to 5 in that case, in this particular case. Where does that come from? Oh, come on, you guys know this. I picked that number on purpose, 3 and 4. 3 plus 4 equals 5. Isn't 5 the hypotenuse of that? You guys remember the Pythagorean theorem? A squared plus b squared equals c squared. You learned that in grade 9. 3 squared plus 4 squared equals 5 squared. So sometimes 3 plus 4 equals 7. Sometimes 3 plus 4 equals 1. Sometimes it equals minus 1. Sometimes it equals 5. Or if you've got some crazy angle that's not a 90-degree angle there, it could equal something entirely different. Okay, the bottom line is now the rules all change. Now we have to add vectors together. And the rules of vector addition, not crazy hard, but they're slightly more complicated than the rules of scalar addition that you learn in grade 1, and the rules of vector addition in one dimension, right? Positive, negative, that you learn in grade 5 or grade 6. Now we've got to add vectors together that are at different directions, north and west, or south and east. So the normal rules of addition don't apply. 3 plus 4 does not, notice we're not saying it does not equal 7. It does not necessarily equal 7. If it's 3 to the north and 4 to the north, then it equals 7. Here's the goal when we're adding vectors in 2 dimensions, like we just showed you with that diagram, east and south, or north and west. We've got to get what we call a vector diagram. It's a right-angled triangle. I'll explain what a vector diagram is in a minute. That vector diagram should be a right-angled triangle. And then we're going to use trigonometry. Sine, cos, tan, the Pythagorean theorem. All of those things that in grade 9 you hated. But the good news is you're smarter now than you were in grade 9. So you're not going to have a big trouble with them this year. Here's the rules of drawing a vector diagram. Rule number 1. We have to draw each vector that we're adding, each number, as a simple line segment with an arrow. So for instance, if you've got a vector that's 3 to the east, you're going to draw it like this. 3 to the east, with a little arrow pointing to the east. If you've got a vector that's 4 to the west, then we're going to draw it this way. A little line segment with an arrow on the end of it pointing to the west, with a little number 4 that shows me the magnitude of it. If we've got a vector that's 2 to the south, I might draw it like this. 1 to the north might be like this. Notice that each of these vectors are line segments, each with an arrow pointing in the direction of that vector, each labeled when we can. And notice one more thing. They're drawn more or less to scale. We're not going to measure it with a ruler, but we're going to eyeball it as much as we can to a proper scale. The vector that's 2 to the south is about twice as long as the one that's 1 to the north. The one that's 4 to the west is about twice as long as the one that's 2 to the south. The one that's 3 to the east is about 3 times as long as the one that's 1 to the north. Draw it more or less to scale. Now, when we go to draw the diagram adding these together, we have to draw them what we call front to back, or sometimes we call it head to tail. This is the front of a vector. This is another front. This is another front, or the head of a vector. This is the back of a vector, the back, the back, the back, or the tails of vectors. We have to draw a vector diagram so that one vector is drawn such that its front will join up with the back of the next one, or its head will match up with the tail of the next one. So for instance, if you're drawing 3 to the east and 4 to the south, we have to draw it like this, or you could draw it like this. In both cases there, we have our vectors drawn properly, okay, with an arrow indicating direction, more or less to scale. And in both cases, we've drawn it front of one vector to the back of the next vector. The front of one vector to the back of the next vector. So front to back or head to tail. Louis? I'm sorry? If you have a north and a south in the same one? Oh, I see what you're saying. I see what you're saying. You know, let's worry about that in a little bit. Okay, it's a good question, but we'll talk about that in a few minutes, okay? Now, the sum of the vectors, which is really what we're trying to find here, right? We're trying to add numbers together. We're trying to add numbers together that don't happen to be, you know, scalars or all in one direction. The sum of the vectors is what we call the resultant vector. And it's drawn, notice Not from front to back, it's drawn from back to front. So the resultant vector, or the sum of these vectors, is drawn from back to front, or from back to front. Doesn't matter which one you do there, okay? They both work there. The bottom line is, got to be drawn from back to front. So the ones you're trying to add, front to back. The ones that you're, the answer, the resultant vector, is drawn from back to front. Opposite to the rest of them. All right. Let's just do these ones as a group here, these quick examples, okay? Add the following vectors. 10 meters plus 20 meters to the north. Well, Lewis asked a question a minute ago. He says, what do you do if you're trying to draw a vector diagram and it's all in the same direction, right? North and north, or north and south, or what do you? Well, the reality is you don't actually really need to draw a vector diagram for those, because we can just do those algebraically, right? 10 to the north, 20 to the north gives me 30 to the north, right? 10 to the north and 20 to the south gives me negative 10, or 10 to the south. We don't need the vector diagram there, right? Technically, Lewis, we could draw it, right? 10 to the north, 20 to the south. We could draw it, but it's not very helpful to do that, right? But now it is. When you see 10 to the north and 20 to the east, it becomes helpful to draw that diagram. So let's do that. 10 to the north, 20 to the east. Is that okay? Could I have also drawn it like this? Is that okay? How about like this? One of these three vector diagrams is wrong. Which one is it? Yep. The third one. Why is the third one wrong? What's wrong? Back to back. Good. You cannot go back to back. It doesn't work. This one works because it's front to back. This one works because it's front to back. This one doesn't work because it's back to back. So let's get rid of that one. First two still work. The resultant vector, if you remember, the resultant vector is drawn from back to front, or from start to finish. Now, how would you solve for that? How would you solve for the resultant vector? Let's do this in a different color there. How would you solve for the red resultant vector there? Yep, Pythagorean theorem. A squared plus b squared equals c squared. Or in other words, c is equal to the square root of a squared plus b squared. So it's the square root of 10 squared plus 20 squared. 10 squared is 100. 20 squared is 400. 100 plus 400 is 500. Square root of 500 is about 24-ish. 22.36. Thank you, Derek. Let's solve for the red one, or for the green one, I should say. It's equal to 20 squared plus 10 squared, square rooted. R is equal to, lo and behold, 22.36. If I had asked Tyler, I didn't ask him this question, but if I had said, as a follow-up to the question that I asked Tyler a little while ago, what's 3 plus 4? He said 7. If I had to follow that up with what's 4 plus 3, Tyler would have said 7, right? It doesn't matter what order we add numbers in when we're adding scalars, right? It also doesn't matter what order we add numbers in when we're adding vectors. 10 plus 20 gives me 22.36, or 20 plus 10 equals 22.36. Same answer, right? Let's do the bottom one. 10 to the west, 20 to the south. Well, we've got a couple of options here. A couple of options for drawing this one out. Yep. Yep. Good question. if you didn't hear Haley's question, she said, would it be 22.36 northeast? We actually do need a direction because it's a vector, right? We're adding two vectors together to get a vector, so we do need a direction. It wouldn't be northeast. It would be at an angle, but we'll deal with that in a little while, okay? I don't want to deal with that one quite yet. Okay? You're right, there needs to be an angle, but it wouldn't be northeast. It would have to be some kind of angle that we'll deal with shortly. Okay, let's look at this one. I'm going to draw 4 possibilities. Okay, and I want you to put, okay, in your own little mind, well, no, not your own little mind, your own big mind, a check mark, a little check mark, or a little X, okay, beside each one. First one. Does that work for us? What's wrong with the first one? Back to back. It's drawn back to back. We can't do that. Okay? It's not the rules. Like, we can't do that if we want to add these two correctly. Second one, does that work? Right, does that one work? Yeah, front to back, right? Front, back. That works. Third one, does that work? Yes, it's drawn front to back. Even though it's the opposite order, it still works. Fourth one, does that work? Tony? No, how come? It's front to front, doesn't work. So let's get rid of those ones. Okay, let's get rid of the two that don't work there for us. Now let's start the resultant vector. The resultant vector is always drawn from back to front. Those both work? Sure they do. Let's get the resultant vector for the red one. So square root of 10 squared plus 20 squared equals, lo and behold, 22.36. Green one? Lo and behold, 22.36. So if we add 10 plus 20 at right angles to each other, it doesn't matter what the directions are. They're always going to give us 22.36. Now, Haley pointed out a minute ago that we also do need that direction with it, right? They're all going to be different directions. Okay? Right now, we'll just deal with the magnitude of the answer, 22.36. Yep. No, that's a good question too, Lewis, but no, you don't have to do that. Negative 10 squared plus negative 20 squared. In the end, we have to indicate directions somehow when we're adding vectors together. The diagram does it just fine. The diagram takes care of that, doing that. Having said that, if you did make it negative 10 squared, as long as you squared not the 10, but the negative 10, and as long as you squared not the 20, but the negative 20, what would you get? 22.36, right? Because negative 10 squared is positive 100. Okay. So you can do that. I would suggest not doing it, though, because if you do, then what might happen at some point is you forget to put the bracket in, and you go negative 10 squared, and you get negative 100 then, because your calculator will square just the number that's right in front of it, right? All right? Let me give you one to work on here, guys. Let's say 20 meters to the west. Let's say 50 meters to the south. I want you to add those together. Starting with a vector diagram, then with the Pythagorean theorem to get the magnitude of my answer. Okay, we need a volunteer to come up to the board and draw the first vector here, the 20 meters to the west. Lewis, you're up. As soon as Lewis is done, we need a second volunteer to come up and draw the second vector, 50 to the south. No, I don't even want the full diagram. All I want is 20 meters to the west. Okay, Lewis has got the easy one. 20 meters to the west. Is he right, by the way? Looks good. All right. Who's up next to draw the second one, 50 to the south? Okay. Is he right? 50 to the south? Yeah, he's right. Couple things there that I noticed. One, he's drawn it front to back, which is correct. And two, he's drawn the 50 meters a little bit more than twice as long as the 20 meters, right? So more or less to scale. Good? Somebody come up and draw the resultant vector, please. The combined vector. Do that one in red. This person gets to use the nice red color. Or, hey, listen, you could even, if you want, pick a different color. Whatever color you want. If you want to come up and volunteer to do this. All right. Let's go. Is that right? A little boring for the color. I was hoping he might pick a little bit something a little bit brighter than the red, since I encouraged him to do that, but that's okay. Is he right? What's wrong with it? Yeah. Should it be the other way around? Back to front? Or sorry, front to back? No, it actually should be back to front. Yeah. The resultant vector is always drawn backwards, right? The first two vectors, front to back. The resultant vector, right, it's back to back or front to front here. Okay, from start to finish. Make sense? Okay, let's solve for this now. The resultant vector there is going to be the square root of 50 squared plus 20 squared. What does that equal? Yep. 53.85. Now, just out of curiosity, did anybody draw like this? Anybody draw like that? Yes. What'd you get for your resultant vector? 53.85. Exact same thing. Of course it's going to be the exact same thing. It's like saying 3 plus 4 is equal to 7. 4 plus 3 is equal to 7. Of course you're going to get the same thing. Doesn't matter what order you add them in, okay, any more than it does for scalars. 53.85 is the correct answer there. Got it? All right. Well, what happens if we have three vectors? 3 plus 4 plus 1 equals 8 if we're adding scalars. But what's 3 plus 4 plus 1 equal if we're adding vectors? Well, in order to do this, we have to use what we call vector components. I'm going to show you how to use vector components with a couple examples here. And then we'll wrap it up for the day. We want to add 25 meters to the north, 20 meters to the east, and then 30 meters to the north. Here's 25 to the north. Here's 20 to the east, and here's 30 to the north. The resultant vector, notice front to back, front to back. The resultant vector is drawn from start to finish, right there. That's a correct resultant vector, even though it looks a little bit odd right now. But what we don't have right now is a simple right-angled triangle where we can do the Pythagorean theorem. In fact, you can't have any triangle when you have four sides. Okay, four sides doesn't make a triangle. Yep. Great, good point. Couldn't you just add the 30 and the 25? In effect, that's what we're going to do. But I want you to do it the way that I'm going to do it here, okay, because it becomes a matter of structure. Later on, when you get more complicated questions, I want you to be familiar with the structure that we use to solve this problem. So don't take a shortcut on this. We're going to break this into x and y. This is x, this is y. How much of that first vector, 25, is x? How much of it is this way? How much of that 25 is that way? I'll give you a hint. It's a one-word answer. How much of that 25 is on the x-axis? One-word answer, and it starts with n. Jacob? Son? Pardon me? None of it. None of it, right? Is that what you said? 0. Okay? None of that 25 is on the x-axis. How much of the 20 is on the x-axis? 20. All of it. How much of the 30 is on the x-axis? Jacob? None. Let's add these up. 20. So the total x is 20. Let's do the y's now. How much of that 25 is on the y-axis? 25. How much of that 20 is on the y-axis? None of it. How much of the 30 is on the y-axis? All of it. Let's add these up. 55, 20 plus 55. Well, it's not 75. Now what we have to do is draw another diagram, but this time it's going to be a simple right-angled diagram. 20 to the east, 55 to the north. And the resultant vector is going to be drawn in red there. And we can find that by just doing the Pythagorean theorem again. 20 squared plus 55 squared. So the goal was to get a right angle triangle. Remember, the very first line you wrote down here, I think, in this whole notes on adding vectors together was the goal was to get a right angle triangle. Okay? Now we have that. In the examples that we did a few minutes ago, we had it right away. This time we didn't. We got a funny looking diagram up here that we changed into a simple looking diagram that we saw down there that we know what to do with because we've done it a few times already. So get the components. Jacob said, right off the top, he said, couldn't you just combine the 25 and the 30? The answer is yes. Okay, and that's in effect what we did, right? We just took a little longer to do that than Jacob did in his head, right? As they get more complicated, it's going to become more and more difficult to just do that shortcut in your head, right? And you're going to want to be familiar with the structure so that you get them all right. What if we get 13 vectors that we have to add together? And one of them's not north, one of them's at 16 degrees. And then it becomes really challenging to do that without the structure. All right? All right, guys, that's it for today. I will ask you actually right now for the next few minutes or for homework tonight to finish that second example. Just that question right there. We'll take a look at that one tomorrow. That's it for today, guys.